the logic. Are you there?
Yes, I am.
Yeah, what I want is for us to be able to understand the logic properly, so that when you're developing things in terms of the program that you're developing in our ladders, ranks, and all that stuff, we understand exactly what's going on. So that's what we want to focus the time on now. So here we have let's identify what we have. So this what we have. This is an AND gate, not so. This.
I can't see the pointer.
For real? Can you see where I'm writing? Can you see that?
Yes, I can.
Okay. Yeah, so that's me pointing. So this is an AND gate.
Okay.
This is a NOT gate. Sorry, an OR gate. This is another AND gate. Okay. Actually, let me just do this so that we are moving together. Let me do this. And let me do this. Let me pick that. Okay. So what I was saying is that this.
Are you able to make the screen a bit bigger?
It's smaller. You can see me. You can see me while it's just in the screen.
Yes.
Okay, then that's a problem. Let's change the layout. You don't have to see me.
So I can tap out as well. The video. I can switch off my video.
Yes. Okay, so when you have switched off your video, how good is it now?
It's the same for now. Doesn't change.
Okay. How good is it? Still the same?
Still the same.
Okay. Probably what is happening here is a layout issue. So you need to change the layout on your end. Maybe let me click here. Is it still the same?
I'm trying to. Okay, it's better. I've changed the layout. Put full screen on my.
Okay. Yes. Thank
you. It's okay now.
Thank you, sir. You can proceed. So we have these various gates that we are seeing here. Okay. We have these various gates that you're seeing here. So AND gate, OR gate, AND gate, AND gate. This is a NOR gate. Okay. This is another AND gate. This is another AND gate. This is another NOR. So this is exclusive OR gate, like that. So what you're saying is, in order for you to understand properly, before you start developing your ladder logic, you need to be able to, kind of relate what you're seeing in terms of the logic that you know vis-a-vis the representation of that logic in ladder system. So ladder logic will look like this. Remember what we said was that each rung, so a rung is more or less like each instruction level. Okay. So each rung is actually a logical operation. That's what he said. So if you look at what you have here, you have got your input A, input B, and output Y. This will evaluate to true or false, 0 or 1. That's what it will evaluate to. Now, it will be 1 when A is true and B is true, then this will be 1. Okay, like that. Now, if we are talking about O, O will look like what you're seeing here. It's either this or this, like that. If we are talking about NOT, this is how it's going to look like. So NOT will look like that. So instead of the normally open contact, we are going to have a normally closed contact. That's a representation of a knot. Then if we proceed, we go to NANDI. So it means that NANDI should be both knot, okay, like that. Then if we go to NO, it's a knot and knot, okay? So basically, if we look at exclusive OR, it will look like that. Exclusive NO, it will also look like this. So understanding these basics like that would really help how you evaluate ladder logic. Okay, it will really help how you evaluate ladder logic like that. So I think I shared this in the WhatsApp group. Huh?
I didn't see it.
Yeah, probably just didn't check. It's there.
Oh, okay.
Yeah, because even when I was adding it to this slide, I was getting from there. So what I would implore you to do is to be able to understand these logic gates and understand their counterpart in ladder logic. When you understand this, it will be very easy for you to build ladder logic programs. Because for instance, if I told you to say, when sensor A is high, like that, and when button B is high, that's when the motor runs. Okay, so if I told you that, it will be very easy for you if you understand this, because you now know to say, okay, so the sensor has to be high, the button has to be pushed, that's when the motor runs. So this sensor could be, let's say, a voltage sensor, because what you're looking at is that there should be presence of power in order for the motor to run. So when the sensor says, yes, there is power, and always when you're starting things, even in a home or in an industry, we look if there's power. You can't go and start pushing a motor if there's no power. So if you, and how do we know? We know this through maybe light indicators. So this sensor A might just be a simple VT that just says, yeah, there's power. Now, when the VT says there's power and you push the button, that's when the motor will run. So that will look like the first AND ladder logic representation, like here. Your motor will be represented by this, coil, and these contacts will represent the nature of the sensor A and the nature of the sensor B, like that. And that will become easier for you to be able to do that. So this would be very, very important for you to just go through and understand properly. When you understand this, work will become very easier for you. Okay.
Okay. I'll go through.
It's self-explanatory. There's nothing really much to explain there. So your job is just to go through. Oh, so AND gate. What does AND gate mean in logic sense? Oh, so its representation in ladder logic means this. Then that will be quite easier for you, like that. So let's go back to our silo project. So let's go back to our silo project. Just confirm if you can still see the screen.
Yes, I can.
Okay. Sorry, I just want to hide this away from my face. So if we have this arrangement like this, okay, let me just open Silo Simulator. Thank you. And let me go online and let me download that particular program into the silo. And let me go into the run state.
So what I'm seeing is the same presentation where there are logic gates.
Okay. Sorry.
Ladder.
Okay.
There's gate and ladder logic.
Okay, sorry. Let me just Let me just do something here. Okay. So share, stop sharing, then share. And then we want to share a window. We are interested in sharing this specific window. Please confirm if you can see the window that we are sharing.
Yes, I can.
Okay, thank you. So this is what we were doing the other time. Okay, when both of us were tired. So
Yes.
I'll just stop this and reset everything. Let me first of all go offline. Now I'm offline. I can reset the simulation by resetting the simulation like that. Okay, you click on simulation and then you scroll all the way down. You have reset simulation. So you click on that. Now, after you have reset the simulation in that particular manner, we want to finish where we ended. Now, in order for us to understand this properly, we'll just start and go through the program up to the far end. Is that okay?
It's okay.
Okay, so you remember the arrangement, yeah? So just before we can proceed, I just want to comment on some things here. This interface here, this interface that you're seeing here, comes from this button here that says simulation. So this software has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 simulations. So we'll go through all these so that we understand. Now, the idea is that the more we are going through this, the more you are grasping the concepts behind the logic of PLCs and the automation arrangement. Now, this is very basic. I should mention that because there are a lot of other things that are abstracted or which we are not considering. Now, after we finish this, we understand. Then we can now transition to Siemens DIA portal, and then, or we can transition to, Fanex Contact AutoWorks software. So that now we are dealing with a real-world automation tool. That's what we need to do. So we are starting basics. We're starting with basics. We understand. So the purpose of us doing all this simulation is not now to say that we understand the automation and PLCs. No. It's for us now to master the basics of ladder logic programming. When this is closed, when this is open, when this contact is like this, when the sensor is open, closed, when the sensor is normally open, what does that mean? That's what we are doing here, is to cement our theory. That's what we are trying to do. So we would want, when you are alone, you open your simulation program, practice as much as you can like that, because that's the only way you're going to cement the understanding. So let's go ahead. Now that you have understood where we get there, these are settings. Under settings, you just enable, do you want sound to be there? Do you want to enable Malin, that's old guy that shows there? Do you want to enable screensaver and all these other things? Then on comms is where you choose to go online to see who is active, to download your program that you have developed here into the PLC. Okay. Then other than that, we have got the help. Under the help, you find student exercises. So when maybe our class grows to a good number of people, I'll start giving exercises so that now you're able to go and answer those and bring them back. So I've got student exercises here. We've got a calculator that you can use to calculate the timing, the run time, and the scan time, and all those things, which is there. Then we've got this one is a Rockwell RS Logics instruction set. So you can download that there. This one is ABSLC instruction set reference manual. Okay. And then below there, we'll have an online check for availability of Logics Pro updates. And then we have got about the Logic Pro itself, like that. So that's what we have there. The most important is for you to be able to get this student exercise and start playing with it. Next time when we meet, we're going to start from here so that whatever tasks that we are solving are coming from here in that particular case. The Rockwell RX Logics instruction set reference manual, these together will just help you to understand which instructions, what does those instructions means and all that. It's a PDF manual that you can read to just perfect. Now, these are real world instructions. They are not simulation based, real world instructions written by the owners of, Rockwell PLCs, like that. So that's what you get there. Now, when you come here, this will just allow you to create, when you click there, it will allow you to create a new, if you're working on some new processor type that you want to work with, you give the processor the name there and all those stuff. And as you can see here, we have got different processors. So you'd want to give your processor you're working with a name. Now, the one that I'm working with is a processor emulation, as you can see. Because
so when you click, I'm not seeing the drop-down menus.
I know why.
Just in the page as it is.
Yes, okay. I know I am the problem. I'm solving that just in a second. I needed to give you the entire screen. Okay. All right. So let me go ahead and click. When you click here on new, okay, like that, what you are doing here, you can select the processor type that you're dealing with, and you can give that a type, a name here. Okay. So for instance, I can call this as emulation, like that. Now, I'm choosing PLC Logic Pro processor emulation because it's a simulation. But if you're working in real life, you would find you can choose 1747L553. Okay, this is a real processor on that you find on a type of a PLC that you have purchased. And as you could see, this is a very high-end particular PLC because you could see its memory is about 64 kilobytes. That's a lot of memory that you would find there. Okay, so here you could see what driver link you are using, the kind of drivers, okay, like that. Here you could see number of processor nodes that you are using. Here you could see who is active, okay, like that. Here you could see reply timeout. So you could be able to see all that. All that is important information. For now, because we're in simulation, we're not caring much about that. But if you are, let me just go ahead and open what I've closed once more. Okay. So if you are working with a real PLC, so you need to be able to see how many inputs do I have, how much memory do I have, which processor type, because that software that you'll be using to program it need to know exactly which PLC it is talking to. What kind of memory does that PLC have, and other things. Just like when you're programming a microcontroller, you select to say, I'm now programming an Arduino Uno or an Arduino Nano, or I'm programming an XMC 4200 and things like that. You select specifically which one you're programming, okay? So that the software can be able to recognize the hardware. That's the importance of what I was just showing you. This is a save button, just like in Word and then other editors. That's a save. Here where you have got file, or if you click on it, it will allow you to create a new project. If I click on that, it will allow me to create a new project, okay, in that particular manner. So in this case, we are just using what we did last week, okay. Then edit just allows you to insert a rung and all that. If you want to insert a rung, if we click on insert a rung, you'd be able to see that you can be able to add a new rung as we go like that. Then simulation, I've already discussed this, but below here would be point of interest. If you want to reset your simulation, you click on reset simulation down here. If you want to reset your timers and counters in your PLC, you click here. Just in case there's something that you are checking, you just want to say, I just want to clear the timers and counters so that I can start from 0. You click there. If you want to clear all data fields or data tables through there, you click here. You see how that will be important as we go. Settings, we have covered that. Comms, we have already covered that. So now, when you are using a real processor, a PLC rather, you'll be able to see which driver are you using. Now here we are using a simulated driver. It's a CSS DDE link. But for you, if you are using, you know, an actual PLC, you'll be able to see something different. Now, this is a simulated environment. I have emphasized the purpose is for us to familiarize ourselves with automation, with logic, how do you develop a program, how certain arrangement might look like in real life and things like that. So you practice as much as possible so that when you go into the actual environment of automation, such as the TIA portal for Siemens, you'd be able to realize that actually you are familiar with certain concepts that has to do with a PLC, ladder logic, as well as the automation concepts. So let's proceed. Now, this here is our HMI here. This is our HMI. Why? Because this is where we are interacting with our system, human-machine interface. So this is what we are using to interface ourselves to this system. Because if you click on a motor, nothing is going to happen there. Just like in real life, when you go and touch a motor itself, there's nothing that's going to happen. Okay? You need to be able to wire a button to this motor, and that button you sit in a panel. Now, that panel, we are going to call it a control panel. This, in automation, we use human-machine interfaces, such as an HMI. So this is our HMI here. What are we having? We're having this control button. We can be able to push to put it on C, on B, on A. We're able to start, we're able to stop, we're able to observe the run light, the fuel light, and the full light. So basically, this is our HMI.
The selections A, B, C, what do they mean?
So these selections might mean what you have said. You'd say, I want my PLC to run in C mode or in B mode. So these are basically modes like that. Okay. So maybe in B mode, it's an automated mode. In A mode, it's a semi-automated. It depends with the way you're going to write your program. But these are just different mode selections that you can be able to develop yourself.
Okay.
Yes. So I'm going to go online by clicking either on comms. So you can go online by doing two things. You see here where it says offline. I can this drop down. I can just choose to say download to the PLC, okay? Or I can choose to go online, or I can choose to go offline. Now I'm choosing to go online. So now I'm online, and you can see my PLC actually appears there, okay? I can do the same by just going to comms.
When you say you're online, what do you mean?
It means now that the PLC is now connected to the system.
Okay.
Yes. So imagine you have a cable. You get your cable, you connect it to the programming device or to your automation infrastructure. Now that means now you have introduced the PLC, and the PLC being the heart of the automation, it then means now your PLC has come online. That's what that means. In real life, that might mean the PLC is powered, the PLC is connected, it's communicating, and all that things. Okay?
Okay.
Yeah. So now that your PLC is connected, then now we can download the program. This program that you have developed, we can now flash it into the PLC or load it into the PLC. So we click on download. So it's downloading the program P code. It has downloaded. It has finished. Now we can go to run. Okay. So now in this case, our PLC now is running. As you can see, it's doing its scan cycles there, as you can see there. You can see, okay, scans per second, 60 scans per second, 61 scans per second, and you can see all that stuff happening there. If you would also be able to see that the values here are being updated. Okay, 022, that's on your input card. You know, this is on your output card, as you can see that. So this is your input module, and this is your output module, like that. If you're on a real PLC, now this means that whatever that is connected to that particular input, output number 6, something is happening to it, something connected to input there, something is happening, and all that. So now we get to here, we want to click on start. So when we click on start like that, okay, you'll be able to see. Now I want to be able to, I want to be pausing. So we can pause by going to step. So when you go on step, we have paused. When you go back to run, it will require you to click start and then it will continue. So that's what we can do there. Now let's study what's happening. What's happening here is that we are in continuous mode operation. So this is a continuous mode operation. If you go into, so this mode in which you are running, you can be able to, if you programmed a manual mode, you could be able to move in different modes by changing these selectors like that. But we have not done anything. The only thing we have done is an automatic operation mode in A. So what's happening? When you push the button here, the system will start running. Now, when it says system will start running, we have energized the coil onto which the motor is connected. Now, when the motor is running, what's happening is this run button will go high, this conveyor belt will start moving. Meaning the box that is on the conveyor belt will start moving. When it reaches here, it hits this proximity sensor. It stops the motor from running. Now, when the motor is deactivated, we activate the solenoid instead. So they just swap. As soon as the motor stops moving, we activate this solenoid. So that now the feeding will start happening. When it is feeding, when it is full, when it's full, this level switch sensor deactivates the solenoid and activates the motor so that it starts moving, so that it takes whatever that you have filled, the material you have filled in the box, to another station or to wherever it's supposed to go. That's what's happening. Let's run through. The first thing, when you push the start button, the motor is activated, it starts running. At the same time, the run button, this button, the run light come on here. And it will remain on forever because the system is running. Whether you are feeling, the system is still running. That's why it is feeding. So that run light will continue being on. Okay? Now, after it hits this proximity sensor, the motor stops running and the solenoid valve is activated. Now, when that solenoid valve is activated, what's going to happen is that it will start filling from this mill. It will start filling. When the material being filled from the mill is full to the brim on the box, the level sensor detects that it is full. What does it do? It deactivates the solenoid and activates the motor. That's all what's happening here. Have we understood the process?
Yes, sir.
Now let's go to the program. Now, when you come to the program, what we learned is that this is a normally open contact. Now, a stop button should be, if you go to your stop button here, it will tell you to say it's a normally closed contact. What does that mean? It means that even if you are not seeing it here that it's normally closed, it's actually normally closed because you are using the address of this particular sensor that is dictating that. Now, because this is normally closed, it means naturally it's allowing current to flow from this point up to this point. Now, when we reach at this point, there's no way that current is going to flow because this is open and this is also open. So what's going to happen is when you push this start button, when you push it, okay, so I'm holding it down. If you can see, when you push it like that, it allows the current to momentarily pass by momentarily closing this contact. When this contact is momentarily closed, it will allow the current now to flow through this rung all the way up to the coil. Now, because this coil shares the same address as this run light contact, what do you think is going to happen? This, it will close also, or it will be in latched state. Why is it going to be in latched state? Because what we learned was that when a PLC scans once, it updates the output. The output will remain in that status until something changes on the input in the second scan cycle. You remember that? So we discussed that the operation cycle or the operation phases of a PLC is 4 stages. Stage 1 is input scan. Now, in this case, it's scanning, have you pressed the button? Is there any button that has been pressed? Is there any changes from the sensors? All the input devices are scanned in that phase 1. In the second phase, what happens? It's execution. Now, execution simply means this particular PLC acts on that particular information. Okay? Now, when the PLC acts on that particular information, before it updates the output status bits, or basically the output, what it's going to do, it will first run some diagnostic tests and communication, just to ensure is everything okay before I update. Have we read any short circuit anywhere? Is our system okay? Is our PLC everything okay? So after it does that, the last stage is to update the status bits. Now, what are the status bits? What you're seeing here, updating those registers, the address, okay? Now, after it updates that, nothing will change. If it said that the light has gone on, the light will remain in the on state, not until the second cycle says that something has changed. Are we following? Now, in this case, I'm laboring to explain so that you understand what latching means. What latching means in this case is that because momentarily this allowed the current to pass, and then this and this has the same address. It means that when the update on the status bit was made, or the register was updated to high, it means that even this one was also closed, or basically it allowed current to pass. Now, because it's depending on the output register, which can only change after something changes on the input scan cycle, it means that this will be forever on, because it's dependent on the output. Only when the output is updated, depending on the changes on the input scan cycle, that's when this is going to change. You have seen that? So what that means is that this will be forever latched. So now it means now we have got a path. Remember, a stop push button is a normally closed, so meaning here the current or the signal is flowing. And when it reaches here, the signal can't go through here because this is open. It will come down here. But now this is latched because of the output. So then we have got a path like that, which is continuous. And as you could see by that yellow light, indication, this is allowing signal to pass. This is allowing signal to pass, and that's allowing signal to pass continuously like that. This is only going to change if something changes on the input. And what's going to cut that flow is the stop push button. If I press the stop push button like that, you'd have seen now that it has cut. Momentarily, it went off and it updated the output status register. So now we are off. Because of that, this will also cut. If I momentarily start, you see that it's again latches continuously like that. That's how you can achieve a latching in ladder logic like that. It's a very important concept to understand. Now remember, we also discussed that each rung has a name or a number or an address. So this is 000, as you can see there. It's a beginning. Now this rung is a logical operation. What that simply means is that when the rung is evaluated logically, it should give you a logical output or a logical, evaluated value. Now that, because it's logic, that value can either be high or low, 0 or 1, true or false. Now, in this particular case, we are seeing that this rung is giving us a true at the end, or a high, or a 1. That's what you're seeing there. Then if we go to the second rung, what do we need to do? What have we achieved in the first run? In the first run, we have achieved two things: to start the system and leave it in the latched state, but also to turn on the run light. That's what you have done. That's what this one is doing. Without it, this light won't go on. Okay? That's what you have done. You have achieved that. Now let's go to the second. We are saying that in the second stage, if the box is not in the fill area, which is this area, or if the box is full, there are two conditions there. If the box is not in the fill area, this is a fill area. If it is not here, or if the box is not full, then energize the converter. That's what we are saying there. The conveyor belt or the conveyor motor, this motor, energize it. Now let's read again. If the box is not where? In the fill area. Or if the box is full, that's only when you're going to energize the conveyor motor. So this first run, all it's doing is to energize the run light. That's it. Okay. Now we are using the run light as means of starting this particular motor. Because the run light is running, then let's start the motor. But in order for us to start the motor, there are two conditions. In order for us to energize the motor or to start the motor, it's the same thing. There are two conditions. You can energize the motor if it is not in the fill area or it is full. That's only when the motor should be able to run. Now, look at what you have done. This, you have brought this one here because we only want this particular motor. Whenever the motor is going to run or to be energized, the run light should be on. So this is guaranteeing that if the motor is running, it means that this is also running. That's what we are doing here.
Your voice is breaking, sir.
Oh, sorry. My voice is breaking.
I think it's the network. Are you able to get me though?
Perfect.
I think my network is okay, but
can you hear me?
I can hear you now.
Okay. Can we proceed?
Yes, so I think you can just repeat the previous statements. I could not get you clearly.
All right. Can you guide where you want me to start?
We did the first run.
Mm-hmm.
Now you were explaining the second set of instructions on the second run.
Okay.
Yes.
So we're saying that our first run is guaranteeing two things. Number one, to start the system by starting the run light. Now, when the run light is running and you have latched that so that it's continuously, because what you are doing here is to demonstrate the continuous operation. Or in other words, we can say an automated operation of the filling. That's what we are achieving. Now, after we achieve that in the first run, the second thing is that we are saying in order for the motor to actually be energized, the light, run light must be on. Or in other words, the system should be running. That's what we are saying. Okay, the system should be running. So we bring this particular contact here to ensure that this run, in order to ensure, why we have brought this contact here is to ensure that the motor can only run when that light is on. That's what you're doing. Now, the next thing that we're saying is that the motor can only be energized on three conditions. Number one, the run light should be on. Number two, the box should not be in the fill area. Number three, the box must be full. So these three conditions is only when the motor can be energized. Which motor? The conveyor motor, this one here. So this motor is driving the conveyor belt. So we are calling it the conveyor motor, this one. Now this conveyor motor can only be energized on 3 conditions. Number 1, the run light must be on, indicating that we have power. Number 2, the box should not be in the fuel area, because if the box is in the fuel area, it means that we are filling the box. Number 3 is that the box must be full. So if the box is full, then it's okay, the conveyor can run to transport the box. So those are the 3 conditions. Now let's interpret them into logic. So we have brought this contact here to guarantee that the run light is on. Okay? Because if we remove this, what that might mean is that this can be energized and it can run even when that is not indicating. That will become a problem because we will not know if our system is running, especially if this conveyor belt is in remote. Okay? So if you are building your HMI, you want to be able to know, even if the motor is 10 kilometers away from your control room, you want to be able to know that actually the system is on by means of this light. This light will be able to show you that. So when the box is in the fuel area, we should not energize the motor. When the box is full, we should energize the motor. So it's not on the fuel area or the box is full. So not in the fuel area. This is a not representation. The not logic in ladder logic is represented like this. Okay? From that cheat sheet I gave you, the not is represented like this. If you remember, I can just go there to quickly show you so that we are moving on the same page. So this is a not. You can see that the not, it's here. You can see this. That's a not. You can see that.
Yeah.
So we are saying the box must not be in the fuel area. So it's a closed contact, normally closed contact like that. So we go back. Now what you're saying here is that if the box is not in the fuel area, so the box is not in the fuel area. How do we know that the box is not in the fuel area? We know that the box is not in the fuel area by means of the proximity sensor. So this sensor senses the proximity of the box to know whether the box is in the fuel area or not. That's why it is strategically positioned at the fuel area, the proximity sensor. Now, what you're seeing here is that if the box is in the proximity sensor, what happens to the proximity? If the box is in the fuel area, the proximity sensor is energized. Now, fundamentally, we agreed that if you energize a normally closed contact, it opens. Okay? So what that means is that by means of this upper rung, or by means of this upper instructions like this, if you follow my cursor from here to the proximity sensor to the output, the motor will disconnect because this is normally closed contact. As soon as the proximity sensor is high, or this is going to be disconnected. That's what's happening. So we have solved the first part. The second part, we are saying if it is full. How do we know if it is full? We just read the level sensor here. Now we are reading this level sensor indirectly because what we know is that if this level sensor here, if this level sensor senses, it triggers the full light. That's what's happening there. We are actually not even reading this sensor directly by itself. No, we are reading it indirectly by using the full light. So what we know is that when this level sensor is triggered by means of the box being full, it triggers the full light. So we said, okay, we'll be reading this sensor indirectly. So when the full light is triggered, it means that the box is full. So when the full light is triggered, we can energize our motor. Let the motor start running because now it's full. And remember, this full light is just triggered momentarily. So it means this will be momentarily closed and then it will allow this to run like that. The motor will run, okay? It will remain running because the other alternative of the or is that this proximity sensor is not hit. So that's what's happening there. Have we understood this run? Now, we move to the next one. If the level is reached, okay, which means this level, if it is reached, what do we want to do? Then latch and hold the full light, okay? We're going to latch and hold the full light to on while the box remains in the fill area. I'll read that again. If the fill level is reached, then latch and hold the fill light on while the box remains in the fill area. So this is what you're doing here. We are saying, since we pick now this sensor itself, we put it here. If the fuel level is reached, okay, meaning full to the brim, okay, like that. So this will close. Now, when this is going to close, what are we expecting is going to happen? We are saying then latch the full light, okay, so that the box remain in the fuel area. That's what you're achieving in this run. Now, if the box is in the fuel area and the box is not full, then energize the fuel valve, which is this one. Okay? Then energize the fuel valve and the fuel light. So we are doing two things. The fuel valve and the fuel light are being energized at the same time. This is why you are seeing we have got the O output. Okay? So it's this or this. So when this is through, this will be energized, this will be energized at the same time. So when the solenoid is energized, the fuel light is also energized, because when the solenoid is energized, this miller is now dropping the material into the box. We want the fuel light to be also on. That's what's happening. Then we are at the far end there. Questions?
I think it's clear. The process is clear.
Okay.
Probably just the aspect of now practicing, but because it's easier, of course, when you're just looking at it. No, the actual part, but the process is clear. So I need my pump to run under 3 conditions. I need the run light to be on. I need it not to be filled, not to be full, and I need the box to be in a specific area.
In the fuel area. So
Yes.
Those are the 3 conditions. In order for you to push the valve, the solenoid valve that pumps the material from the mill, 3 conditions has to be met. So basically here you are AND. This is an AND logic. Okay. So your run light, because the system has to be running, so run light has to be there. Second, it should be in the proximity sensor. It's within the proximity area. So the proximity sensor has to be pushed. Okay? Or has to be high. And the full light must not be on. Because as soon as the full light goes on, it means now it is full, de-energized. Now, basically, reading the full light, we are simply reading the level sensor, not so.
Yeah.
That's what you're doing there. I've got a question that I want you to think about, and then you can come and tell me when we meet. If we changed the full light address, you can see here. You can see this. On the last run, you can see this.
Yes, I can.
Yeah. If we change, because what you're saying here is that we are reading the full light, and you're saying that the full light is being triggered based on the level sensor, not so? If we change this and put the level sensor here, the address of the level sensor, what will be the behavior of this system? Because the level sensor will be triggered also when the material is full, as it has been triggered there. Okay? So if we put it there, when it is high, this we should expect this should also be able to open. But I want you to go and think about that and see how this might be able to behave. So we dismiss the class and we meet next time.
Let me just be clear on the question.
Mm-hmm.
If the full light address
This,
was to be swapped with the level sensor address,
yes.
what would be the reaction?
Mm-hmm. So you are getting this, that's what you are dropping here in that particular manner. You get this is what you put there. Okay? What you're saying is that the full light is going momentarily high when this is high. So pay attention, pay attention. When this turns purple, you see the full light to go on. Okay? And then it goes off. So we're saying if we replace, instead of reading the address of the full light, we read the address of the sensor directly here. What will be the case? All right.
Maybe just a short question.
Yes.
The way the rungs are arranged, is that how the scanning is done?
Yes.
So it starts from top to bottom.
Yes. Yes. Yes.
So us changing the rung, will it really affect our set of instructions and how the system will behave?
It might. It might, because here's an example that you're saying. If you made this to be the value of the input level sensor, yeah, there, if that's a register, you put there the address. What's going to happen is this. Where else are we working with that level input sensor? You notice that you're working with it here. So meaning, when this goes high or something happens to it, that will also affect this, because now these two have the same address. So if you write to that address, you have also written to that address. So yes, it will change.
Okay.
If you pay attention, what's happening here is that when this goes purple, this is being closed here. You can see that. Yeah, this is being closed here. Now, when this is being closed, this will also close at that same particular time. Okay. Now, what that will mean by this closing is, because this is normally closed, this will open if you energize it, but this will do close. So the response will be different. What I want you there is to think, why did we use the full light address and we did not use the sensor directly? Why did we do that? How can we do it in a different way? That's what you're trying to look at in that question I'm asking.
Okay.
Yeah.
So when is the next class?
When is the next class? How many times have we met this week? 2?
This week, I think. Is it 2? Or when last did we?
Yeah, I think that should have been a Thursday.
Thursday last
actually,
week.
No, actually a Tuesday, because Thursday is the one we didn't meet.
Oh, okay.
So we can even meet again tomorrow. So that we just ensure that we cover the 3 times that we need to do in a week. So we can meet again tomorrow. We can create time. We can create time for that. So this is how this is working, like that. So the scanning starts from the top rung. When the top rung is evaluated based on the output, based on the logical operation of the first rung, then we move to the second rung, then we move to the third rung, then we move to the fourth rung, and it goes on like that. Now, when we talk about scan time, we talk about scan time in 2 ways. There's cycle time, there's scan time. So now, how long does one cycle take? That contributes to the total scan time of a PLC. So the question you asked about which runs first. So when this runs, the evaluated logical operation of this affect the second run. For instance, as you could see, the evaluated operational logic of this run light is what you are using to start the second one, if you can see there. Okay. Then when you go to the third one, we are again depending on some on things that we used here, such as you could see this. Okay. This address for the proximity sensor, we are using it here. And then when you get to this point again, we are depending on that same run light of the first one. So these all are somewhat, some rungs are interconnected, they depend on each other, some rungs don't, like that. That's how it works. Just like in other programming languages where we have certain functions that depend on each other, certain functions don't depend on each other, like that. So for instance, a rung can just be responsible for reading a particular level sensor of maybe a dam, like that. It will just be doing that. That's what that rung will be doing. Okay. And then the output of that can be used in another run, you know, and then it keeps going on like that. So that's how this works. Now, if you wrote a 1000 or 999, because you can see we have 3 placeholders there. So if this is a 9, this is a 9, and that's a 9. So 999 rungs can be written within this program. There's a possibility of us achieving that. That will make your scan time to be huge. That's number one, because your program is huge. Okay. Probably you would even need a bigger computer to run that. Secondly, you'd also realize that you consume more memory, because if I save this, what you have done here, it's in KB. But when these rungs go to 999, you find that the memory will be bigger, maybe in MB or in hundreds of KBs. Now, in that case, that's the point we talked about when you're sizing the PLC. You need to be able to know how big your plant is, how big the program might look like, and from there, you estimate the size of the memory for the PLC that you want to buy. So those are just some summaries or recaps that I wanted to point out before we end. So see you maybe tomorrow.
Okay, thank you. See you.
Okay, sure. Thank you.